Welcome to your Chapter 22 lecture, where we're going to talk about the birth of the universe. Throughout this book, we've studied how the matter that's produced in the early universe gradually assembled to make stars, galaxies, and planets. However, we haven't answered one big question yet. Where did the matter itself come from? To answer this question, we need to go beyond the most distant galaxies and even beyond what we can see near the horizon of the universe. We need to go back not just to the origins of matter and energy, but all the way back to the beginning of time itself. As we will see, while many questions about the birth of the universe remain unanswered, we now seem to have some understanding of events that must have unfolded as far back as the first fraction of a second after the Big Bang. So this first section of this chapter is going to focus on the Big Bang theory. Is it really possible for us to study the origin of the entire universe? It's kind of a big question here. Not long ago, before we were able to measure the size and age of the observable universe, this topic was kind of unfit for scientific study. But scientific attitudes began to change with Edwin Hubble's discovery that the universe is expanding, which led to the insight that all things very likely sprang into being at a single moment in time in an event that we have known and come to call the Big Bang. Today, powerful telescopes allow us to view how galaxies have changed over the past 14 billion years and at great distances. We see young galaxies still in the process of forming, and these observations confirm that the universe has been gradually aging. So in this section, we're going to answer the questions: what were conditions like in the early universe, and how did the early universe change with time? Unfortunately, we cannot see back to the very beginning of time to see what the conditions were like in the early universe. But light from the most distant galaxies shows us what the universe looked like when it was a few 100 million years old. Light from earlier times is more difficult to observe because we are looking back to a time before stars existed. Ultimately, we face even a more fundamental problem. The universe is filled with a faint glow of radiation that appears to be remnant heat of the Big Bang. This faint glow is light that has traveled freely through space since the universe was about 380,000 years old, which is when the universe first became transparent to light. Before that time, light could not pass freely through the universe, so there's no possibility of seeing light from earlier times. Just as we must rely on theoretical modeling to determine what the sun is like on the inside, we must use modeling to investigate what the universe was like during its earliest moments. The scientific theory that predicts what the universe was like early in time is called the Big Bang theory. That's the scientific theory of the universe's earliest moments, stating that all matter in our observable universe came into being at a single moment in time in an extremely hot, dense mixture of subatomic particles and radiation. It's based on applying known and tested laws of physics to the idea that everything we see today began as an incredibly hot and dense collection of matter and radiation. The Big Bang theory successfully describes how expansion and cooling of this unimaginably intense mixture of particles and photons could have led to the present universe of stars and galaxies, and it explains several aspects of today's universe with impressive accuracy. Our main goal in this chapter is to understand the evidence supporting the Big Bang theory. But first, we need to explore what the theory tells us about the early universe. Observations demonstrate that the universe is cooling with time as it expands, implying that the early universe must have been extremely hot and dense. And we know that because the universe today is cooling as it expands. So this figure here on the slide shows us how the temperature of the universe has changed with time. For most of the universe's history, even back to times just minutes after the Big Bang, conditions were no more extreme than those found in the many places in the universe today, such as in the interiors of stars. Therefore, we can understand them with the same laws of physics that we applied throughout most of our book and throughout most of our class. However, at very early times, temperatures were so high that different processes came into play. So this image here is showing us that the early universe was hot and dense. Over time, it cooled and expanded to kind of where we are at our present day conditions. The universe was so hot during the first few seconds that photons could actually transform themselves into matter and vice versa, in accordance with Einstein's formula, E equals mc squared. Reactions that create and destroy matter are now relatively rare in the universe at large. One such reaction of this type, where photons are converted into particles and vice versa, is the creation or destruction of an electron-anti-electron pair. When two photons collide with a total energy greater than twice the mass energy of an electron, they can create two brand new particles, a negatively charged electron and its positively charged twin that we call an anti-electron, or sometimes that's referred to as a positron. The electron is a particle of matter, and the anti-electron is a particle of antimatter. The reaction that creates an electron-anti-electron pair can also run in reverse. When an electron and an anti-electron meet, like we see in the bottom image here, they annihilate each other totally, transforming all of their mass energy back into photon energy. In order to conserve both energy and momentum, an annihilation reaction must produce two photons instead of one. The early universe, therefore, was filled with an extremely hot and dense blend of photons, matter, and antimatter that were converting furiously back and forth. So we're seeing that the early universe had photons, matter, and antimatter that went through particle creation and particle annihilation cycles, which is what we've described in these two images on this slide here. To understand the changes that happened in the early universe, it helps us to think of them in terms of forces. Everything that happens in the universe today is governed by four distinct forces: gravity, electromagnetism, the strong force, and the weak force. We've already encountered examples of each of these forces in action, and now we're going to go through and explain each one of these forces in a little bit more detail. First, let's talk about gravity. Gravity is the most familiar of the four forces to us. Gravity provides the glue that holds our planet, stars, and galaxies together. Next, we're going to discuss the electromagnetic force. The electromagnetic force depends on the electrical charge of a particle instead of its mass, and the electromagnetic force is stronger than gravity. So the electromagnetic force is the force between particles in atoms and molecules, and it's the force responsible for all chemical and biological reactions. So it's talking about the charge of electrons. The existence of both positive and negative electrical charges causes the electromagnetic force to lose out to gravity on large scales, even though both forces decline with distance by the inverse square law. Most large objects in space, like planets and stars, are electrically neutral, making the electromagnetic force unimportant on that scale. Gravity, therefore, becomes the dominant force for these objects because more mass always means more gravity. So we typically see the electromagnetic force for more things like particles and things smaller scale. The strong and weak forces operate only over extremely short distances. So these are important within atomic nuclei, but not on larger scales. The strong force binds protons and neutrons together in atomic nuclei. And then the weak force plays a crucial role in nuclear reactions. such as fission and fusion. And this is the only force besides gravity that affects weakly interacting particles like neutrinos. So in this slide, we just kind of went through quickly a general overview of these 4 forces that are known in the universe to exist today. So we saw that all these 4 forces behave differently from one another, but the current models of fundamental physics predict that they are just different aspects of a smaller number of fundamental forces. These models predict that at the high temperatures that happened in the early universe, these 4 forces would not have been as distinct as they are today. Experiments have shown that the electromagnetic and weak forces lose their separate identities under conditions of very high temperatures and merge together to form one single force that we call the electroweak force. At even higher temperatures and energies, the electroweak force may merge with the strong force and ultimately gravity. Models that predict the merger of the electroweak and strong forces are called grand unified theories, or GUTS for short. So when we have the strong force plus the electroweak force, we get what we call the GUT force. The merger of the strong, weak, and electromagnetic forces is this GUT force. And many physicists suspect that at even higher energies, the GUT force and gravity merge into a single force that we call the superforce that governs the behavior of everything. Current ideas for linking all 4 forces go by names that include supersymmetry, superstrings, supergravity, and what we also can call the theory of everything. If these ideas are correct, then the universe was governed solely by the superforce in the first instant after the Big Bang. As the universe expanded and cooled, the superforce split into gravity and the GUT force, which then split further into the strong and electroweak forces. Ultimately, they split into the electromagnetic and weak force, and ultimately, over time, all forces became distinct. As we'll see shortly, these changes in fundamental forces probably occurred before the universe was 1/10 of a billionth of a second old. So the splitting of these forces happened very quickly. Now we want to look at how did the early universe change with time. The Big Bang Theory uses scientific understanding of particles and forces to actually reconstruct the history of the universe. Here we're going to outline this history as a series of eras, which are simply just time periods. So an era is just a time period. Each era is distinguished from the next by some major change in physical conditions as the universe cools. So we're going to find it useful to refer to this timeline here and notice that the time scale runs by powers of 10, which means that early eras were very brief, even though it looks more spread out on this figure here. For example, it would take us longer to read this chapter in the book than it took for the universe to go through the first 5 eras that we're going to talk about. So they look like they're larger, but actually a lot of them happen very quickly. So we're going to look at how the universe changed by looking at these eras, which are simply just periods of time. The first era after the Big Bang is called the Planck era, named for physicist Max Planck. It represents times before the universe was 10 to the negative 43 seconds old. So this is very early in the universe. According to the laws of quantum mechanics, there should have been substantial energy fluctuations from point to point during this early time. Because energy and mass are equivalent, Einstein's theory of general relativity tells us that these energy fluctuations must have generated a rapidly changing gravitational field that would have randomly warped space and time. These fluctuations are predicted to have been so large that our current understanding of physics is inadequate to describe what might have been happening. All four forces are thought to merge into the single unified superforce at temperatures above 10 to the 32 Kelvin. These are the temperatures that happened during this Planck era. The Planck era would have been a time of ultimate simplicity, when just one single force operated in nature. And it came to an end when the temperature dropped low enough for gravity to become distinct from the other three forces, which were still merged as the gut force. So it started as one single force, that superforce. By the end of the Planck era, we had the gut force and gravity as our two forces. The next era is called the gut era, named for the grand unified theories that predict the merger of the strong, weak, and electromagnetic forces into a single gut force at temperatures above 10 to the 29 Kelvin. The gut era was a time where we had two forces. We had gravity and the gut force. This time came to an end when the gut force split into the strong and electroweak forces, which happened when the universe was a mere 10 to the negative 38 seconds old. So this is actually less than a trillionth of a second. If the grand unifying theories are correct, the freezing out of the strong and electroweak forces may have released an enormous amount of energy, causing a sudden and dramatic expansion of the universe that we're going to call inflation. In a mere 10 to the negative 36 seconds, pieces of the universe the size of an atomic nucleus may have grown to the size of our solar system. So the gut era had this big inflation period. Next up is the electroweak era. The splitting of the gut force marked the beginning of an era during which three distinct forces operated. Now we had gravity, the strong force, and the electroweak force. We call this time era the electroweak era, indicating that the electromagnetic and weak forces were still merged together. The universe continued to expand and cool throughout the electroweak era, dropping to a temperature of 10 to the 15 Kelvin when it reached an age of 10 to the negative 10 seconds. This temperature is still 100 million times hotter than the temperature in the core of the sun today, but it was low enough for the electromagnetic and weak forces to freeze out from the electroweak force. So towards the end of this, we now had all four forces that now were forever distinct in the universe. So now gravity, the strong force, the weak force, and the electromagnetic force were all separate forces. Now we're going to look at an era that we're going to call the particle era. As long as the universe was hot enough for the spontaneous creation and annihilation of particles to continue, the total number of particles was roughly in balance with the total number of photons. Once it became too cool for the spontaneous exchange of matter and energy to continue, photons became the dominant form of energy in the universe. The particle era came to an end when the universe reached an age of 1 millisecond, which is 0.001 seconds. At this point, the temperature had fallen to 10 to the 12 Kelvin, and it was no longer hot enough for protons and antiprotons to be produced. For every billion antiprotons in the early universe, there must have been about 1,000,000,001 protons. That is, for each 1 billion protons and antiprotons that annihilated each other, at the end of the particle era, one single proton was left over. The eras that we discussed so far all occurred within the first 0.001 seconds of the universe's existence. This is less than the time that it takes us to blink an eye. At this point, the protons and neutrons left over after the annihilation of antimatter began to fuse and make heavier nuclei, leading us to what we call the era of nucleosynthesis. However, the temperature of the universe remained so high that gamma rays blasted apart most of those nuclei as fast as they formed. This dance of fusion and demolition marked the era of nucleosynthesis, which ended when the universe was about 5 minutes old. By this time, density in the expanding universe had dropped so much that fusion no longer occurred, even though the temperature was still about 1 billion Kelvin, which is much hotter than the temperature of the sun's core. When fusion ended at the end of the era of nucleosynthesis, the chemical content of the universe was 75% hydrogen and 25% helium, with trace amounts of deuterium, which is hydrogen plus a neutron, and lithium, which was the next heaviest element after hydrogen and helium. Except for the small proportion of matter that stars made into heavier elements, the chemical composition of the universe remains the same today. After fusion ceased, the universe consisted of a very hot plasma of hydrogen nuclei, helium nuclei, and free electrons, leading us to a time that we call the era of nuclei. The era of nuclei came to an end when the expanding universe was about 380,000 years old. At this point, the temperature had fallen to about 3,000 Kelvin, which is half the temperature of the sun's surface today. Hydrogen and helium nuclei finally captured electrons for good, forming stable neutral atoms for the first time. With electrons now bound into atoms, the universe became transparent as if a thick fog had suddenly lifted. Photons that were formerly trapped among electrons began to stream freely across the universe. So we've already discussed the rest of the universe's history in earlier chapters. The end of the era of nuclei marked the beginning of the era of atoms, when the universe consisted of a mixture of neutral atoms and plasma along with a large number of photons. Because the density of matter in the universe differed slightly from place to place, gravity slowly drew atoms and plasma into higher density regions, which assembled into protogalactic clouds. Stars then formed in these clouds, and clouds subsequently merged to form galaxies, leading us to the era of galaxies. The first full-fledged galaxies had formed by the time that the universe was about 1 billion years old, beginning what we call the era of galaxies, which continues to this day. Generation after generation of star formation in galaxies steadily builds our elements heavier than helium and incorporates them into our newer star systems. Some of these star systems develop planets, and on at least one of these planets, life bursts into being a few billion years ago. Now, here we are kind of thinking about all of the past of the history of the universe. So in this section, we learned what the conditions were like in the early universe. The early universe was hot and dense and had a lot of radiation that produced particle-antiparticle pairs and vice versa. The universe also was changing with time. As the universe cooled and expanded, particle production stopped, leaving matter instead of antimatter. Fusion then turned the remaining neutrons into helium, and radiation freely traveled after the formation of atoms. In the rest of this chapter, we're going to discuss the evidence that supports the history of the universe as the Big Bang Theory describes it. So in this section, we're talking about the evidence for the Big Bang. Like any scientific theory, the Big Bang Theory is a model of nature designed to explain a set of observations. The model was inspired by Edwin Hubble's observation that the universe is expanding, which implies that the universe must have been much denser and hotter in the past. So in this section, we're going to learn how observations of the cosmic microwave background support the Big Bang Theory, and how abundances of elements support the Big Bang Theory. Like any scientific model, the Big Bang model had to make testable predictions about other observable features of the universe. And it has gained wide scientific acceptance because of two major predictions that have been verified. So here's the primary evidence for the Big Bang Theory. First, the Big Bang Theory predicts that the radiation that began to stream across the universe at the end of the era of nuclei should still be present today. Sure enough, we find that the universe is filled with what we call cosmic microwave background. This is the remnant radiation from the Big Bang that we still detect today using radio telescopes that are sensitive to microwaves. Our second primary evidence is that the Big Bang Theory predicts that some of the original hydrogen in the universe should have fused into helium during the era of nucleosynthesis. Observations of the actual helium content of the universe closely match the predicted amount of helium. So we see these are our two main points of evidence for the Big Bang: that we've detected leftover radiation and the abundance of helium and other light elements in the universe. So first we're going to look at the observations of the cosmic microwave background and how they support the Big Bang Theory. The discovery of the cosmic microwave background was announced in 1965. Arno Penzias and Robert Wilson were two physicists working at Bell Laboratories in New Jersey, and they were calibrating a sensitive microwave antenna that was designed for satellite communications. Microwaves fall into the radio portion of the electromagnetic spectrum. So they kept finding this unexpected noise in every measurement they made. The noise was the same no matter where they pointed their antenna, indicating that this noise came from all directions in the sky. So this ruled out any possibility that it came from one object or one specific place on Earth. Meanwhile, physicists at nearby Princeton University were busy calculating the expected characteristics of the radiation left over from the heat of the Big Bang. They concluded that if the Big Bang had really occurred, this radiation should be permeating the entire universe and should be detectable with a microwave antenna. So the Princeton group met up with Penzias and Wilson to compare notes, and both teams soon realized that the noise from the Bell Labs antenna was the predicted microwave background. This is the first strong evidence that the Big Bang really happened. In fact, Penzias and Wilson received a Nobel Prize in 1978 for their discovery. So the cosmic microwave background is the radiation left over from the Big Bang, and that was detected by microwave antenna in 1965. When we observe the cosmic microwave background, we are essentially seeing back to the end of the era of nuclei, when the universe was only 380,000 years old. The Big Bang Theory predicts that the cosmic microwave background should have an essentially perfect thermal radiation spectrum because it came from the heat of the universe itself. Moreover, the theory predicts the approximate wavelength at which this thermal radiation spectrum should peak. As we talked about earlier in the semester, the theory tells us that the radiation of the cosmic microwave background broke free when the universe cooled to a temperature of about 3,000 Kelvin, which is similar to the surface temperature of a red giant star. The spectrum of the cosmic microwave background, therefore, should have originally peaked at a wavelength of about 1,000 nanometers, just like the thermal radiation from a red star. Because the universe has since expanded by a factor of 1,000, the wavelengths of these photons should by now have stretched to about 1,000 times their original lengths. We therefore would expect the peak wavelength of the cosmic microwave background now to be about a millimeter in the microwave portion of the spectrum and correspond to a temperature of a few degrees above absolute zero. So what we see in this image here is that the cosmic microwave background has a perfect thermal radiation spectrum with a peak corresponding to a temperature of 2.73 Kelvin. So we're seeing the observed spectrum of the cosmic microwave background closely matches the theoretical model. So here are some detailed kind of baby pictures of the structure of the universe that we can look at. Now we're going to look at how the abundances of elements also support the Big Bang Theory. The Big Bang Theory also solves what was previously another long-standing astronomical problem, the origin of cosmic helium. Everywhere in the universe, about 3/4 of the mass of ordinary matter, not including dark matter, is hydrogen and 1/4 is helium. The Milky Way's helium fraction is about 28%, and no galaxy has a helium fraction lower than 25%. Although helium is produced by hydrogen fusion in stars, calculations show that this production can account only for a small proportion of the total observed helium. Therefore, we can conclude that the majority of the helium in the universe must have already been present in the protogalactic clouds that preceded the formations of galaxies. The Big Bang Theory makes a specific prediction about the helium abundance. As we discussed earlier, the theory explains the existence of helium as a consequence of fusion that occurred during the era of nucleosynthesis, when the universe itself was hot enough to fuse hydrogen into helium. Combining the current microwave background temperature of 2.73 Kelvin with the number of protons that we observe in the universe tells us precisely how hot the universe must have been in the distant past, allowing scientists to calculate exactly how much helium should have been made. The result is 25% helium, which is another impressive success of the Big Bang Theory. So why didn't the Big Bang produce heavier elements? By the time stable helium nuclei formed, which was when the universe was about 1 minute old, the temperature and density of the rapidly expanding universe had already dropped too far for a process like carbon production, which is when 3 helium nuclei fuse into a carbon nucleus, to occur. Reactions between protons, deuterium nuclei, and helium were still possible, but most of these reactions led nowhere. In particular, fusing 2 helium-4 nuclei results in a nucleus that is unstable and falls apart in a fraction of a second, as does fusing a proton to a helium-4 nucleus. A few reactions involving hydrogen-3, which is also known as tritium, or helium-3, can create long-lasting nuclei. For example, fusing helium-4 and hydrogen-3 produces lithium-7. However, the contributions of these reactions to the overall composition of the universe were minor because hydrogen-3 and helium-3 were so rare. Models of element production in the early universe show that before the cooling of the universe shut off fusion entirely, such reactions generated only trace amounts of lithium, which is the next heavier element after helium. Aside from hydrogen, helium, and lithium, all other elements were forged much later in the nuclear furnaces of stars. So the fact that the Big Bang Theory predicts about 25% helium by mass matches the predictions made by the Big Bang Theory. So in this section, we learned about how observations of the cosmic microwave background support the Big Bang. So we can actually observe with a radio telescope the radiation left over from the Big Bang, which we call the cosmic microwave background. We also learned that observations of helium and other light elements agree with predictions for fusion that we saw in the Big Bang. And now in this section, we are going to talk about the Big Bang and inflation. When we discussed the eras of the universe earlier in this chapter, we noted that the universe is thought to have undergone a sudden and dramatic expansion that we call inflation, which may have occurred at the end of the Gut era when the universe was 10 to the negative 38 seconds old. In some models of inflation, the dramatic expansion can happen later, up until the end of the electroweak era. This idea was first emerged in 1981 when physicist Alan Guth was considering the consequences of the separation of the strong force from the gut force that marked the end of the Gut era. Some theories of high energy physics predict that this separation of forces would have released enormous amounts of energy, and Guth realized that this energy might have caused a short period of inflation. He found that in a mere 10 to the negative 36 seconds, inflation could have caused the universe to expand by a factor of 10 to the 30. So as strange as this idea might sound, it appears to explain several mysterious features of our present-day universe. Recent evidence from detailed studies of the cosmic microwave background has provided support for the hypothesis that an early period of inflation really occurred. So we're going to look at, in this section, the key features of the universe that are explained with inflation and talk about, did inflation really happen? So we're going to start with the key features of the universe explained by inflation. The Big Bang Theory has gained wide acceptance because of the strong evidence from the cosmic microwave background and the abundance of helium in the universe. However, without inflation, the theory leaves several major features of our universe unexplained. The three most pressing questions and mysteries that we need to explain are: where does the structure of the universe come from? Why is the overall distribution of matter so uniform? And why is the density of the universe so close to the critical density? Taking a scientific approach to the early universe demands that we seek answers to these questions that rely on natural processes. And the hypothesis of inflation can actually provide the answers and solve all three of these mysteries. So if we assume inflation occurred, we find that density enhancements, large-scale uniformity, and flat geometry are all natural and expected consequences. We're going to start with density enhancements. To understand how inflation explains the origin of density enhancements that led to our galaxies, we need to recognize a special feature of energy fields. Lab-tested principles of quantum mechanics tells us that on very small scales, the energy fields at any point in space are always fluctuating. The distribution of energy throughout space, therefore, is slightly irregular even in a complete vacuum. The tiny quantum ripples that are the irregularities can be characterized by a wavelength that corresponds to their size. In principle, the quantum ripples in the very early universe could have been the seeds for density enhancements that later grew into galaxies. However, the original wavelengths of these original ripples were too small to explain density enhancements like those we see imprinted on the cosmic microwave background. Inflation, though, would have dramatically increased the wavelengths of these quantum fluctuations. The rapid growth of the universe during the period of inflation would have stretched the tiny ripples from a size that's smaller than an atomic nucleus to the size of our solar system. That would make them large enough to become the density enhancements that our galaxies and larger structures later formed from. If that's the case, then these large-scale structures that we see in today's universe started as tiny quantum fluctuations before the period of inflation began. The remarkable uniformity of the cosmic microwave background might at first seem natural, but with further thought, it actually becomes a little bit more difficult to explain. Imagine if you were observing the cosmic microwave background in a certain part of the sky. You are seeing microwaves that have traveled through the universe since the end of the era of nuclei, just about 380,000 years after the Big Bang. So what we're seeing is a region of the universe as it was some 14 billion years ago, when the universe was only about 380,000 years old. Now imagine turning around and looking at the background radiation coming from the opposite direction. You're also seeing this region at an age of 380,000 years, and it looks virtually identical in temperature and density. The surprising part is that these two regions are billions of light years apart on opposite sides of our observable universe, and that we're seeing them as they were when they were only 380,000 years old. They can't possibly have exchanged light or any other information because a signal traveling at the speed of light has not had time to travel from one region to the other. So the question is, how come they have the same temperature and density? How can microwave temperatures be identical on opposite sides of the sky? The inflation hypothesis answers this question by saying that even though the two regions cannot have had any contact since the time of inflation, they were in contact prior to that time. Before the onset of inflation, when the universe was 10 to the negative 38 seconds old, The two regions were less than 10 to the negative 38 light seconds away from each other. Radiation traveling at the speed of light would have had time to bounce between the two regions, and this exchange of energy equalized their temperatures and density. Inflation then pushed these equalized regions to much greater distances far out of contact with each other. In essence, inflation opens up a huge gap in space between objects that were once close together. So these regions that are now on opposite sides of the sky were once close together before inflation pushed them apart. Now we're going to try to answer the third question, which asks us why the overall geometry of the universe is flat. To understand this idea, we need to consider the geometry of the universe in more detail. We need to remember that Einstein's general theory of relativity tells us that the presence of matter can curve the structure of space-time. We can't visualize this curvature in all three dimensions of space or in all four dimensions of space-time, but we can detect its presence by its effects on how light travels throughout the universe. Although the curvature of the universe can vary from place to place, the universe as a whole must have some kind of overall shape to it. Almost any shape is possible, but all the possibilities fall into just three general categories. Using analogies to objects that we can see in three dimensions, scientists refer to these three categories of shape as flat, spherical, and saddle. According to general relativity, the overall geometry depends on the average density of matter and energy in the universe. And the geometry can be flat only if the combined density of matter plus energy is equal to a value that we call the critical density. Critical density is the average density for the entire universe that marks the boundary between a universe that will recollapse and one that will expand forever. If the universe's average density is less than the critical density, then the overall shape is saddle-shaped. If the average density is greater than the critical density, then the average overall geometry is spherical. If the density equals the critical density, then the overall shape is flat. So we see as the geometry of the universe is going to be closely related to the density of matter and energy. Inflation can explain why the overall geometry is so close to being flat, which means that our average density is pretty much equal to the critical density. In terms of Einstein's theory, the effect of inflation on space-time curvature is similar to the flattening of a balloon's surface when we blow into the balloon. The flattening of space caused by inflation would have been so enormous that any curvature the universe might have had previously would be noticeable only on size scales larger than that of the observable universe. Inflation, therefore, makes the overall geometry of the universe flat, which means that overall, density of matter plus energy is very close to the critical density. So our universe has that relatively flat shape to it. So we've seen that inflation offers natural answers to our three questions about the universe. But did inflation really happen? Well, we can't directly observe the universe at the very time when inflation is thought to have occurred. Nevertheless, we can test the idea of inflation through careful studies of the cosmic microwave background. Scientists are only beginning to make observations that test inflation, but the findings to date are consistent with the idea that an early inflation episode made the universe uniform and flat, while planting the seeds of structure formation. The strongest tests of inflation to date come from studying the patterns of temperature differences in the cosmic microwave background, and in particular, the maps of the cosmic microwave background made by the WAMP and Planck satellites. Remember, these maps are only going to show us tiny temperature differences that correspond to density variations in the universe at the end of an era of nuclei, when the universe was about 380,000 years old. However, models of inflation predict that these density enhancements were created much earlier, when inflation caused tiny quantum ripples to expand into seeds of structure. Moreover, detailed models of inflation predict how density enhancements should have been distributed in the early universe, and this allows scientists to calculate the angular separation that we should observe among temperature variations in the cosmic microwave background. So, for example, if the universe is precisely flat as inflation predicts it to be, then the largest temperature differences in the cosmic microwave background should be separated by an average of 1 degree. Careful observations of the temperature variations in the microwave background can tell us about the structure of the universe at that very early time. So this graph shows us how temperature differences between patches of sky in the cosmic microwave background depend on the angular separations of these patches on the celestial sphere. The dots represent data from observations by Planck and other microwave telescopes, and the red curves show us the inflation-based model that best fits the observations. Notice how well that red model line fits the data. The same model also makes specific predictions about other characteristics of our universe, like its composition and age, that also agree very well with the observations we've seen. The general agreement between models and observations provides us with persuasive evidence in favor of the Big Bang in general, and also inspires confidence in the hypothesis of inflation. So some seeds that we've inferred from the cosmic microwave background is that our overall geometry is flat, which means that our total mass and energy equals the critical density. Ordinary matter makes up 5% of everything in our universe. The total matter is about 32% of the total, with some being dark matter and a bigger proportion being dark energy. And the age of the universe is about 14 billion years old. So we see a really excellent agreement with models involving inflation and observations in our present-day universe. In this section, we learned about some key features of the universe that we can explain by inflation. We learned about the origin of structure, the smoothness of universe on large scales, and the nearly critical density of the universe. They're all explained by inflation. We learned that the structure of the universe comes from inflated quantum ripples. The observable universe became smooth before inflation when it was very tiny, and that inflation flattened the curvature of space, bringing the expansion rate into balance with the overall density of mass energy. And we also answered the question, did inflation really occur? We can compare structures we see in detailed observations of the microwave background with predictions for the seeds that should have been planted by inflation. So far, our observations of the universe agree well with the models in which inflation planted these seeds. The bottom line is that, all things considered, inflation does a remarkable job of explaining features of our universe that are otherwise unaccounted for in the Big Bang Theory. Many astronomers and physicists suspect that some process akin to inflation did affect the early universe, but the details of the interaction between high-energy particle physics and the evolving universe remain unclear. If these details can be worked out successfully, we face an amazing prospect, a real breakthrough in our understanding of the very smallest particles, achieved by studying the universe on the largest observable scales. Finally, in the last section of this chapter, we are going to observe the Big Bang for ourselves. You might occasionally read an article in a newspaper or magazine questioning whether the Big Bang really happened. We will never be able to prove with an absolute certainty that the Big Bang Theory is correct. However, no one has come up with any other model of the universe that so successfully explains so much of what we see. As we've discussed, the Big Bang model makes specific predictions that we have observationally verified, including predictions about the characteristics of the cosmic microwave background and the composition of the universe. It also naturally explains many other features of the universe. So far, we know of nothing that is inconsistent with the Big Bang model. In this section, we're going to explore why the darkness of the night sky is evidence for the Big Bang. So we don't need to accept everything that we've learned in this course without question. Next time we're thinking about the origins of the universe, you guys could actually do an experiment yourself. Go outside on a clear night and look at the sky and ask yourself why the sky is dark. So why is the darkness of the night sky evidence for the Big Bang? If the universe were infinite, unchanging, and everywhere the same, then the entire night sky would blaze as brightly as the sun. Johannes Kepler is one of the first people to reach this conclusion. We now refer to the idea as Olbers' paradox after German astronomer Heinrich Olbers. Olbers' paradox is a paradox that points out that if the universe were infinite in age and size, with stars found throughout the universe, then the sky would not be dark at night. The night sky is dark because the universe changes with time. As we look out into space, we're looking back to a time when there were no stars. Big picture point here is that the universe changes with time. So why is the darkness of the night sky evidence for the Big Bang? Well, if the universe were eternal, unchanging, and everywhere, the entire night sky would be covered with stars. But we know that's not the case. The night sky is actually dark because we're seeing back to a time where there were no stars. So this wraps up chapter 22, where we talked about the birth of the universe. So now our big picture that we keep mentioning every chapter is extending all the way back to the earliest moments in time. When we're thinking about the birth of the universe that we learned in this chapter, here's some big picture ideas for you to keep in mind. Predicting conditions in the early universe is straightforward as long as we know how matter and energy behave under the extreme conditions that the birth of the universe took place in. Our current understanding of physics allows us to reconstruct the conditions thought to have prevailed in the universe back to the first 10 to the negative 10 seconds of its existence. Our understanding is less certain back to 10 to the negative 38 seconds. And beyond 10 to the negative 43 seconds, we run up against the present limits of our human knowledge. Although it might sound strange for us to talk about the universe during its first fraction of a second, our ideas about the Big Bang rest on a solid foundation of observational, experimental, and theoretical evidence. We cannot say without absolute certainty that the Big Bang really happened, but no other model has so successfully explained how our universe came to be as it is. So the Big Bang theory is our theory for the birth of the universe. So this wraps up chapter 22. Make sure you guys check out our online course site for all of the course content and assignments associated with this chapter.